Welcome to today's webinar. My name is Joe Sanders. I'm an applications engineer at M2 Technologies, and my specialty is manufacturing applications. During today's event, we'll discuss modern efficient roughing. This is going to include a live demonstration of EdgeCam's waveform roughing technology. We'll show milling, turning, and also mill turn applications. We appreciate your interest in today's topic and for carving out a few minutes. This is a live web event, and we look forward to your questions. Phones are muted during the presentation, and we'll open it up for questions and answers afterwards. If you notice your GoToMeeting panel, it does have a questions tab, which you can use to submit questions. We anticipate the live presentations will be around 30 minutes, and if you're unable to stay, please submit your questions using the GoToMeeting panel so that we can follow up with you later. Hey, let's start with talking about what is this thing called waveform roughing. Waveform roughing is a modern high-speed roughing strategy. This was introduced to EdgeCam in 2012. So it's been around for some time in the EdgeCam software, and there's many folks in the industry that talk about, there's a variety of terms that are thrown out, but many of the terms point to the same thing in the idea that we're maintaining a constant tool load. And there's some advantages to that. One is that tool life is improved. We can often cut much deeper and faster than traditional cutting techniques. And with things like the chip thinning effect of the cutting path, we're able to achieve higher overall feed rates without stalling the tool or creating more cutting pressures on it. So if you could look at the examples on the left, the top images show the high-speed roughing waveform tool path, and the lower examples show the more traditional geometric type collapse shapes that have often been used in CAM software or perhaps on machine programming and other techniques. And while the lower images of the traditional stuff certainly have been used for a long time in work, they cause some machining challenges that techniques like waveform solves. So at the end of the day, what we're trying to do is have better tool performance, reduce the machining time, and be less stressful on the machine. Let's do a quick comparison. So we have a screen image of a typical what we call prismatic part, so some simple pockets, and the green path that you see is where the center of the tool is going to operate. So that's the center tool path. You can imagine how this will sound at the machine. As the tool moves into the corner areas, we've put some red flags or stars on the areas where the tool load gets heavy. As the tool pushes into corners, the load is very heavy there. We would hear that out of the machine. There's also abrupt redirections in some cases for the machine moving in one direction out to another, and that's obviously not desirable at all under high-speed machining. We compare that to waveform roughing, shown on the right. The path here looks much different. And the idea behind the path is to have tangent roll in and roll out to tool path as it enters and leaves material, to have a consistent tool load, and to allow us to achieve the material removal rates that the tool is capable of, and also to avoid sharp redirections to tool path so that we can truly use high-speed machining techniques. By the way, this doesn't require a quote-unquote high-speed machining center. This works very effectively on a wide range of machine tools with a wide range of cutting tools, and we'll be demonstrating that as we go through this quick presentation today. So as it comes to milling, the advantages of waveform are listed here. If you think about the prismatic part here where we have a block of material and need to do some milling of some open scallops and also a closed pocket. On the open scallops, the tool can start off the part and work its way in. We see how the tool would roll into the edge, shown in the red colors. Well, when we're inside the pocket, the tool can't roll into the edge, and what happens is instead there's a ramp entry. When you coil the ramp up in a circle, it's a helical entry, and so you see the helical entry that's used there, the helical plunge to open up the pocket center. For many customers, this eliminates the need for pilot hole drilling. or the choice between, do I want to drill a pilot hole or do I just want to push the tool straight down into material, which really isn't ideal. While the path that you see on the screen looks kind of strange, at the end of the day, what that's doing is it's imitating straight line cutting. So if we took a tool and we ran a tool simply along a single edge, once the tool entered material, the tool load would stay constant. We could watch the spindle load meter on the machine. We could listen to the machine. We could watch the chips. The chip formation is constant because the tool is cutting in a straight line. Waveform imitates that. So it's kind of like taking the spaghetti of a straight line and curling it up in a way that maintains that tool load. One of the advantages of this, in addition to maintaining the constant tool load and the cutting performance benefits we're going to get, is that intermediate cuts are reduced. We're not trying to just collapse the shape geometrically and wind up with these little areas that kind of work all by themselves in a corner. So the effect is that you'll see the tools engaged longer in the material without lifting up. There's obviously the benefits of smooth tangent tool path, which lends to high-speed machining. And this technique is able to be used not just on 2D prismatic parts like we have here, but also on 3D contour mill applications. So customers that may be in the tooling or mold and die, aerospace machining, complex prismatic work, as well as complex 3D work, yes, this is perfect for all of that. One of the secrets to the tool path is consistent tool engagement. So if we think about the challenge of traditional cutting, shown in the images at the top, as a geometric collapse type pattern heads into an internal corner, the tool load actually changes and gets heavier. That graphic may help show that, but if you've listened to a machine cutting with traditional tool path, you hear it. We know that the machine's going to stall in those areas, and so we take steps to mitigate that, which might be to lower the overall speed and feed, or to try to lower the speed and feed just in those heavy areas. But the reality is that the tool load just increased significantly. On an outside cut, the tool load actually decreases. Well, that's a problem of geometric collapse, but with EdgeCam's waveform technique, the tool path is actually adjusted when it's built to maintain the constant tool load. And so we see that while the path looks a little bit strange in the sense that we're used to seeing geometric collapses, and this is not a geometric collapse, this is very intentional, with the result that constant chip thickness and tool load is maintained without having to increase or decrease cutting feed rates to do that. Now there's benefits on the turning side as well. So EdgeCam's Waveform Roughing has been around since 2012. There's a lot of field experience that we've gained collectively in the EdgeCam community with that. And the development team has integrated what they've learned from that into the Waveform Rough Turn cycle, which was introduced at EdgeCam 2015 R1. This cycle applies the proven high-speed machining techniques for turning applications. Now in milling, we often cite the benefits and they allow us to achieve super high feeds and speeds compared to what we were doing before, and things work great. In turning, the benefit isn't always in higher feeds and speeds because we may be in a situation where we can't really rotate the part in the chuck much faster than it was before. But there are still excellent benefits to that. One of them is that you have really good chip control, really good chip breakage. We've heard from many customers that as they use this for certain types of groove applications, for example, in the past with traditional cutting techniques, they would have big stringy chips that in some cases wouldn't fit out through the chip conveyor, and the machine would have to be stopped, and someone has to manually clean the chips out of the chip conveyor. Obviously a job no one wants to do, it impacts production. With Waveform, the chips break off nice and small, no problems at all. So it's not just machinability, but improved chip control and chip breakage, and also increased tool life. And we'll get into some of the reasons for that. The example we have shown on the screen here has a simple groove, and in that groove you can see how the tool rolls its way in and rolls its way out. Compare that to the typical approaches of pushing a tool straight in with a typical plunge groove. or maybe a side groove technique where the tool plunges in and machines sideways. While those techniques do remove material, they introduce cutting stresses that can be very difficult in some materials or some part shapes, and certainly not ideal for a tool. So where would we use Waveform Rough Turn? A groove application like this is certainly a great place to start. But we also want you to consider turning applications. If you think about the part that we show here as a second part, in this turning application, we have the ability to use a single tool and to let that tool remove material efficiently in all the areas that you see here. We'll be showing you both of these part examples and what the tool path technique does there. So let's go have a look at the software and how Waveform works. I'm going to begin with a milling example. And the part that I have here on the screen is a real simple pocket. That pocket is cut with a 3/8 inch end mill. And I have two machining setups or sequences here in the part, one with traditional roughing and one with waveform. Let's start by looking at the one with the traditional cutting. I'll turn off the machine simulation and focus just on the part. As the tool comes into view, you're going to see this traditional geometric collapse start by helixing in, and then the big paths, which we know the tool is buried in, 100% engagement. As the tool then goes to machine the other areas, imagine what this will sound like at the machine. We'll hear the tool load changing significantly during the longer cuts where the engagement's pretty good, and then heading into corners where the engagement gets heavy, and the transitional moves between the geometric collapses where the load changes again, and in some cases the cutting direction changes a little bit abruptly. So we're all used to the tool path of this type of application, and perhaps have, without even realizing it, lived with some of the results of what that looks like, where running speeds and feeds lower than what the manufacturer recommended. Let's switch over to the sequence where we're using Waveform Rough Turning by comparison. Same part, same tool. Let's look at what happens. As the tool comes into view, you'll see that the tool still takes a helix approach. Because we're cutting much deeper, that helix is actually tapered to help with chip evacuation and prevent any deflection. But then as the tool opens the shape up, notice that it maintains a much smaller engagement. Actually, that was intentional, but it maintains the tool engagement as it cuts, and it stays down in material as it repositions for the next pass. That's done at a high feed rate so as not to waste time. But as the software begins to then open the shape up, I'll speed this up a little bit. You'll notice that as the tool heads into the corner areas, it stays in those corner areas to work them out completely before going into the next one. This is a much more efficient path. It eliminates the tool path fragmenting, a lot of the tool lift up, and other things that would be typical with a geometric collapse type shape. Okay, so let's go back and take a look at how do we create waveform. I'm going to begin with using a quick comparison where we're going to look at the cycle time right now. Might be hard to see on the overhead, but that's 7 minutes and 14 seconds, so a little bit over 7 minutes. In terms of cutting rates, with this 3/8 cutter, we were using 25 inches a minute. For XY feed, 10 for down feed, and 5,000 RPM. In order to use waveform, we use EdgeCam's roughing cycle. It's the same roughing command that we use for typical machining strategies such as concentric, or lace cutting, or spiral cutting. So we'll switch to waveform. First and foremost, I want to point out that because this is just another option in roughing, it gives the CAM user a tremendous amount of flexibility. What if I have an old part that was programmed under an older strategy and we want to now update to a waveform strategy? Piece of cake. We just go in and change waveform. We've heard of some customers that have long-running jobs, parts that have run for many years, and the machinists on the shop floor like the performance of waveform so much that they will come in and ask the programming staff can they quickly reprogram the job for waveform, because they know that all you need to do is change the strategy. So let's begin with that. We'll change the strategy to waveform, leave everything else the way it was, and press OK. The first thing that we see, if I shut off the display of the machine and look straight down at the workpiece, and maybe turn off the tool display for right now as well. Notice that the path that we have here has a much different shape now than what we had before. So I'll undo one time. Now, guess that there was a couple things there, but at any rate, we'll redo that. So we see the path very different now than what we had before under traditional. Let's do a quick cycle time. When we look at the cycle time, it's now nearly 10 minutes. So we've gone from about 7 minutes to 10 minutes. Why is that? Well, when we switch to waveform, there's a lot more path involved. We now have 1,190 elements or moves compared to 105 with the geometric collapse. So if there's more tool path, it will take longer. But the idea behind waveform is now that we're using a consistent tool engagement, we should be able to move our cutting data to what the tool is capable of. Many tool manufacturers have rethought their feed and speed calculations with techniques like this in play now, and many of them will suggest that we want to use smaller percent step overs, such as 20%. So let's go ahead and use a smaller percent step over. Let's tell the software to look up good high-speed cutting data from our tool library using data we've plugged into there. So the speeds and feeds are optimal for a 20% engagement in this case, and what the tool is capable of in depth in this stainless steel material, or this tool steel, I should say, 700 thousandths of an inch. So with those cutting parameters in place, now let's go look at what the cycle time is. We can notice that now the cycle time has dropped to 4 minutes, 5 seconds, compared to the original just over 7 minutes. So not only have we reduced cycle time, but we're improving cutting performance with the same exact tool. We haven't changed the tool we were using before. We've just improved how we're using it. Right now, though, if we look closely at the path, you can see here that what's happening is the tool has a nice radial engagement, works its way around the part. It's going to come on back out, and then it feeds across to the next pass. So the tool is out of material at that point, but because the software is focused on keeping the tool down on the part, the move is a feed move. We can actually make that a little bit more efficient and introduce a technique called microlift. So I'm going to go in here, and there's a couple of minor options that we can improve waveform. We'll say, yep, we want high feed on what we call the back pass out of material, and I'll allow for 5 thousandths of microlift off the surface. With the microlift, we're not lifting all the way up to clearance plane and coming out of material. We're just lifting off the floor a slight amount, then moving over at a very fast feed rate since we're out of material. Then the tool will switch back to normal cutting feed and come back down. This works very good for high-speed machining, and it will reduce the cycle time further but still keep the tool down. Notice now that the back passes, shown in the dark blue, under a dotted line style to visually indicate that they're a high-speed repositioning move. Notice the back passes linking the tool path. If we go look at the cycle time now is 3 minutes and 46 seconds. So this is a very simple part, and we've made significant improvements to feed and speed calculations. But to go and summarize quickly, the main things that we did were change the strategy to waveform, plug in cutting data, percent step over, cutting rates, and depth of cut suitable for what the tool can actually do when we maintain a good chip load. And then also the minor improvements to keep the tool down and add microlift and high-speed repositioning on the back passes. That's it. Real simple to deploy. Let's switch off to look at a couple of turning applications. So I'm going to go in now and start with looking at face groove applications first. I have a lot of customers that as they begin to explore the waveform and look at perhaps they've got some experience on milling and now they want to try it on the turning side. They ask what kind of an application would be a good one to look for. We always look for grooves with a large radius at the bottom of them. In many cases, customers are already using a full radius groove tool. That's the case here. So when we go out to the machining tab and simulate the path that we have here, you'll notice that, again, keep in mind that what you're seeing is the center point path where we're driving the tool from this red dot. So the blue path that you see is where that dot has to be driven to cut the shape accurately. we see the tool roll into the cut and roll out of the cut. That is exactly what the tool manufacturers recommend. The technique used here is one that the tool manufacturers call trochoidal grooving. So if you've ever seen information about trochoidal grooving recommended for groove applications, EdgeCam's rough waveform turn cycle is the one to use. The requirements are simply that you have a full radius tool, whether that's a full radius groove tool, or a dog bone insert, or a full round insert. When you have a suitable tool, there's a turning cycle for rough waveform turn. It's very simple inputs, very similar to turning, but it produces a much different path. So in this case, we're using a 10 thousandths offset, 10 thousandths inch per rev feed, 600 feet per minute, and a 55 thousandths cut increment or advancement. This is a part that we've actually machined in 4140. So we can see the path here. If we look at this from a simulation standpoint, the post processor that this is hooked up to right now is a twin turret, multi-spindle machining center, but don't be fooled by the multitasking machine. This is a very simple cut. So as we switch into a profile turn view and zoom in on this a bit and play the simulation, as the tool comes into position, we can see that blue full radius cutting tool. We'll see how that tool comes in and very easily rolls the tool in. We've asked the cut to maintain a single cut direction. The software quickly runs the shape and then the finished pass that we've asked for. This is a great application for perhaps your first experience with rough waveform turning. Customers often start with a full radius groove such as this. The name of the cycle that produces this in the software is called rough waveform turn, and there's a reason for that. And the reason is that we don't want you to stop at grooves. This is also capable of turning applications. There are some areas of technology where there's preferences to do what we call bidirectional turning, and also to use full round tools in difficult materials or in difficult geometries. This example here, we have a ball hitch. And again, this is an application that we've done out in the real world. And notice that there are two rough waveform turns with the same tool. If I slow down the cutting rates here and replay that, you'll notice that in the first cut, what we're doing is we're taking the existing material. So you can see the material starting condition. And that tool is being pushed down through the material, working from outside towards center. So intentionally, the cut is a single direction cut designed to push to center. The next cut picks up at that point, and now the tool is allowed to run both directions to remove the material from this captured area. There's only really one way to get into here, from this direction, and this is technically a groove application. With one tool, we're able to machine both segments of this part. That has freed up turret space, which is often a constraining factor in many turning centers, to be able to have other tools available. Think of if we didn't have this technique and we did not have a full radius tool to pursue this with, and the typical turning approaches that would be taken to machine this entire shape. So a good example of using rough waveform turn for what we would call a turning application that might not be the thing we think about when we think about grooves or trochoidal grooving. And then finally, the third application I'd like to show briefly is one where we combine both waveform rough milling and waveform rough turning together in a multitasking turning center. In this case, that happens to be a turning center with live tooling, but it could just as easily be a milling machine with turning capability. EdgeCam can handle multitasking machines and does an excellent job of that. So as we look at the tool path here, I want to point out first the driven tool. It's a face-mounted tool that goes and mills using waveform this scallop, and then after that goes and cuts this pocket. So if we're looking at this from the end-on view, this is a fairly small tool. It's a 1/4 inch tool in a fairly narrow slot. We can see how waveform is able to put the tool into the hole and then mill right across there. Again, this is an application that we have done out in the real world, and with the limits of how many tools are on the turret, it was excellent to be able to helix down into this tight area and have very efficient path that runs this tool right through the shape, machine the outside shape, and get it all done with a single tool. If I switch over to a turn view, normal horizontal turn, we'll go look at tool 5. Here we've got waveform rough turn. We've intentionally split this into 3 different segments, where in the first segment the tool comes into position. You can see the starting stock shape. Some was turned in a previous op, and this tool just feeds across that. Let's speed that up just a little bit. We see the chip thinning effect of a full radius insert. Very good for machining with ceramics and some materials, as well as many groove tool applications. The tool will take the material down until it's reached that step height. I'll stop simulation there. And then we've intentionally split out another cut to now come in. There are a variety of reasons for that, ranging from insert changes in some super difficult applications to just chip control or process control as well. And then a third cut to go attack the small bottom area. So again, a good example of using a combination of both waveform rough turning and milling. Think about your typical 12-station turret on a machining center like this, and the challenges of having to tackle this part without something such as a full round tool with waveform and live tooling. Now, if you have a machining center that doesn't have live tooling, you could still certainly attack a process like this with using waveform rough turn for the turning stuff, and then having another setup that goes and takes care of the milling in a milling machine. Very typical workflow, just simply showing that the software can combine together the high-speed approach of waveform for turning and for milling applications. Okay, let's head back to the PowerPoint for a couple wrap-ups and then to questions. So the first thing I want to point out is the results from a case study that we did. This is all the way back to 2012, but it's still a great case study. We took a part that had a variety of pocketing, and it had a couple tools that were used in it. There's a 3/4 inch 3-flute end mill and a 3/8 inch 4-flute tool. You can see the parameters on the left side for the depth of cut, percent step over, and the feeds and speeds used for a typical pocket. And that was about the ideal cutting rates for that tool in 4140 for the particular piece of geometry. It was running about 43 minutes cycle time. When we used the same exact tool, same geometry with waveform, we achieved a much shorter cycle time on exactly the same part. There was no wear on the tools, chip formation was great, the cutting performance was much better, and look at the cutting rates we were able to achieve. Slightly deeper depth of cut, lighter step over, much higher feeds and speeds with the larger tool, and also with the smaller 3/8 cutter as well. Just a reminder of the face groove and the application we did there, again from the real world. In 4140, with a 5mm groove tool, 55 thousandths of an inch depth of cut at 600 surface feet, and with this one we were able to run up to 24 inches per rev for material removal. There, in turning centers, again, there's often a limit to how comfortable we are as users and machinists at how fast we want to run. Field experience will dictate that, but excellent performance benefits and much faster than traditional cutting methods with excellent performance and chip control. Okay, so final thing before we get to questions. How do we get started with waveform? The waveform technology is available on EdgeCam's mill, turn, and production licenses. Production systems combine mill and turn together into the same license. So as long as you have a standard mill, standard turn, standard production, or higher, maybe advanced or ultimate, you've got waveform already. So if you're getting ready to start using it, just put it to use. Begin using it. For turning tools, you'll need a full radius tool. Could be a groove tool, could be a full radius ball mill, or full radius insert, I should say. And then from there, you just want to think about speeds and feeds. If you do not change the speeds and feeds for what you're used to doing, experiences that waveform, because it builds more path, because its more intelligent path is going to take longer to run. So you really want to reconsider your cutting parameters. In most cases, start with what your tool manufacturer recommends. Our experience is that in many cases we can cut faster, and this is true for both your off-the-shelf tools from maybe MSC, as well as engineered cutters specifically recommended for unique applications. This applies to materials not only from aluminums, but also to superalloys, ceramics, composites, very difficult to machine materials, glass, and so on. Again, same thing, this is just excellent techniques for those kind of materials where a grinding type approach works better than a just push it all out of the way approach. And always start with the tool manufacturer's recommendations. You can often cut faster. Techniques work well on machines that perhaps have limits to their spindle speed and torque, but also works excellent at machines that are well suited to high-speed machining. So our message is put it to use, give it a shot. If you'd like some further assistance with that, in addition to getting you off to a quick start with the EdgeCam software, we also have applications engineering where we can work with you on your company's applications and help really leverage the software potential to solve your challenges. Okay, as we go into wrap up and go into questions, I want to point out the questions area in the chat window. And if you have a question, at M2 Technologies, our sales executives, technical advisors, and support team are available to assist with your software applications, questions, and needs. Reach out and put us to work on your challenges. Don't miss out on the opportunity to connect with M2. Follow us on social media for updates, special announcements, and exclusive promotions. You can also watch helpful videos on our YouTube channel and visit our blog for tricks and tips that will boost your productivity.